All right, let's take some time and review second semester Algebra 2. I've got a document here, a PDF, that I'm going to go through, and I will link to that down in the description of this video. Hopefully this helps you review a lot of the material from second semester Algebra 2. A lot of this stuff is kind of tricky, and it's good to just go through it and remind yourself how you did it, and then hopefully you'll do well on your final exam. So let's jump right in. Number one, it says find all the zeros. Find all the zeros of a polynomial. So those are values where the function spits out 0. That's what a 0 is. So you set it equal to 0, and you factor as you go here. And I notice that this is an x to the fourth and an x to the squared, or second power, and there's no variable right here, so I can't take a greatest common factor out, but this will reverse FOIL into x squared, and then negative 10 and positive 5. See how 5 times negative 10 is negative 50. And then the outside and inside add up to be that middle term there. Now you always keep going. If you see some x squares here, we go ahead and we factor it some more if we can. This one is prime, but we're going to get some imaginary zeros out of that, so you'll see that in a second. This one has a couple zeros in it as well, real zeros. Now neither of these can really factor again, so we're going to set each to 0 separately. This is called the zero product property. Since the product of these two things is equal to 0, we can create two separate equations and solve the two separate equations. So x squared equals 10, x equals plus or minus radical 10 is one of the answers. And then if you subtract 5 here, you get x squared equals negative 5. So now you do the square root on both sides, right? And we're not allowed to have a negative under a square root, so that's where those imaginary numbers that you learned about this year come into play. So x equals plus or minus I radical 5. The 5 doesn't come out of the radical because it is not a perfect square. So we leave the 5 under the radical, but the negative sign that was under the radical turns into that I that you see there. And that's it. So those are the exact answers. Whenever a problem says give exact solutions, that means in terms of a radical, no decimals. No decimals. So that radical 10, we just leave it radical 10. Okay, finding all the zeros of this mess. They don't give you much to go on here, right? They do not tell you what one of the zeros is. Now, if you have a graphing calculator, you could graph this polynomial and find some x-intercepts, and those are zeros. So you could do this graphically. You could also use synthetic division to just try different ones. So what I mean by that is you take this number here at the end, and you think about all the factors of negative 90. So I'm not going to write them all down. Plus or minus 1, plus or minus 2. Plus or minus 5, right? And you keep going. And then you just keep trying those until you get something that has 0 remainder. So if, back in my day, we had to do these without a calculator. So we had to use synthetic division to find the zeros. And it's really just trial and error. So let me show you how I'm going to try a number. So I'm going to try the 0, positive 1. So I take those coefficients, 1, 3, negative 1, 27, and negative 90. Remember how we did this? We took all the coefficients here and we write them over here. And I've got a really good video on synthetic division if you need a reminder on how to do synthetic division. You drop the 1 down, you drop that first one down, and then you multiply these two and write it right there. So 1, and then you add, and you get 4. And now you just keep repeating. 1 times 4 is 4. We write it right here. Whoops. We write it right here. And we add them up. 3, 3, 30, 30. Uh-oh. Why did I say uh-oh? Because there's a remainder. Okay, so if there's a remainder, then that's not going to be one of our zeros. Positive 1 is not one of our zeros. So I'm going to erase this and go back. We're going to try again. We could try negative 1, but let's try 2. I have a feeling maybe this one's going to work. 1, down here. We bring that first digit down. We multiply. We multiply. We get 9. We get 18. And then we get 45. And then, we get 90. Look at that. It goes in cleanly. So 2 goes in there. So what that means is that x minus 2 is a factor. And what's left behind is x to the third plus 5x squared plus 9x plus 45. All of that equals 0. Now, we're going to take this right here and keep going. Now, we already know that 1 doesn't work. And if I remember right, negative 1 doesn't work either. Let's try 5. So I'm going to take these numbers, and I'm going to do this again with 5 now. Because what I'm doing is seeing if this guy right here splits up. And since 45 is divisible by 5, that's why I'm picking that. I'm going to try 5. If that doesn't work, then I'll go for negative 5. Let's see. Drop this down. 5, that is 10, 50. This is not looking good, folks. You see how these numbers just keep getting bigger and bigger. So let's go back and try again with negative 5. It really is just trial and error. Unless you have a graphing calculator, you could be finding the x-intercepts on this thing. Bring the 1 down, and we multiply here. We get negative 5, which is 0, 0, 9, negative 45. There it is. There it is. So that means x squared minus 9 is left over. So we now have x minus 2 times x plus 5. I haven't said this, but remember, you change the sign when you're writing the actual factorization. And then what's left behind was x squared minus 9. Now that splits into x plus 3 and x minus 3. All right, so if you were asked to factor, this is what you'd have. But we were asked to find the zeros. So all the zeros are x equals 2, negative 5. And then plus and minus 3. Those are all the zeros. And I did it without a graphing calculator, but again, finding those x-intercepts probably would be a lot faster if you're allowed to do that on your exam. Okay, so that was number 2. Moving on. If we define a function f as 3 minus x and then a different function g as x squared minus 4, what are we going to do? We're going to find 2 different things. G composed of f, that's what that means, G composed of f, and then f composed of G. So let's work this first one. G composed of f. I like to write it like this for students so they see that we're putting f inside G. So what you start with the outside function, which is G. The G function is the input squared minus 4. I say the word input because I'm going to delete that x and put the f function in there. So I'm putting 3 minus x right inside there. So this is g of f. That's g composed of f. You just leave your answer like that, or maybe you need to FOIL it out and combine like terms. That's fine, but let's just leave it like that for now. And then the other one that they asked us to do was f of g. So the f machine is 3 minus the input. And we're putting g into this one. This is f composed of g. And here we go, x squared minus 4. And there we go. We could leave our answer like that, or we could distribute and combine like terms. All right, number 4, find the inverse. Find the inverse of a function. To find the inverse, you have to switch x and y, because remember, that's what an inverse function does, is it undoes whatever was done by the original function. It's backwards. So we switch x and y, because remember, if a 5 turns into a 1 on f, then on the inverse, a 1 has to turn back into a 5. That's the definition of an inverse word. It just reverses it. Okay, so we're going to switch x and y. We're going to think of this as being y right here. So to solve for the inverse, we write x equals negative 2y plus 4. And then this harkens back to pre-algebra, right? Way back when you're solving super simple equations, and you're just doing it like this, divide by negative 2, divide by negative 2, and we get y equals x minus 4 over negative 2. And you just leave your answer like that. That's called the inverse. You could also write it as g with the little negative 1. It's not an exponent, it's notation. The inverse of g, that's how you say that. Okay, here, this one's a little more difficult. Find the inverse. All right, again, I'm going to switch x and y. There you go. Now what? We got to solve for y. You got to figure out how to get y by itself. So I want to get rid of that negative 5. I'd like to encourage students to think about getting rid of things. So it ends up popping up on the other side. We then square root both sides. Now, whenever you're in the middle of an equation and you find yourself square rooting both sides, that's perfectly fine. Just understand that you now have two possibilities that you have to keep track of, plus or minus x plus 5, and all of that equals y minus 1. I'm then going to add 1 to both sides. So I get 1 plus or minus radical x plus 5 is the inverse of f. So again, how we would write that properly, if this were multiple choice, I'm sure they'd use that notation. All right, so that's the end of page 1. All right, we're moving right along. Find the inverse of this here. Well, let's start by switching x and y. This is going to become x log base 3 of y plus 1 minus 2. All right, so we have to figure out how to get y by itself, and it's stuck inside a logarithm. So first, I think I want to get rid of that negative 2 and just have it pop up on the other side. I'm going to add 2 on both sides, so x plus 2 equals log base 3 of y plus 1. Now I'm going to rewrite it in an exponential form, and we'll talk more about that here in a second. So 3 is the base, so the base is the base. Answers to logs are exponents. So the answer to this log was this. So it goes up as the exponent here. And then what's inside the log goes on the right side. Well, we're really close now. We just subtract 1 on both sides and we have the answer. So let me put it off to the side here. We end up getting the inverse of f is 3 to the x plus 2 power minus a big 1. Or you could put negative 1 plus out front if you'd like to do it that way. All right, so we used exponential form. That's what this is called. We converted log form into exponential form. And we'll have some more problems like that in a moment. All right, find the inverse of this. X equals 7 to the y minus 3 plus 4 power. Okay. Now the y is stuck up in an exponent. So this year, we talked about logarithms and how that's the tool we need in our toolbox to get that variable down so it's no longer in the exponent. Again, I'm going to get rid of that 4 and move it to the other side essentially, but it becomes negative on the left side. Now we're going to rewrite this in log form. Because our variable's in the exponent, we rewrite it in log form. So we write log, and then the base is the base. The base in exponential form becomes the base in log form. And remember, you write this as a small subscript. Okay, a lot of students accidentally write it really big there. So we're going to write it as a small subscript. And then answers to logs are exponents. See, now that y is no longer in an exponent. It's nice and big, and we're going to be able to add 3 on that next step. And then inside the logarithm is x minus 4. We then add 3 on both sides, and we get our answer. I'll write it up here. So the inverse of f is 3 plus log base 7 of x minus 4. There you go. All right, number 8. Determine whether these two are inverses. Now this is where you just pull the trigger on that process. You remember what it is? You find f of g and it needs to come out to be x, and you do a little check mark. And then you do g of f. It needs to come out to be x. And now you've just proven, it's a proof. You've shown that they are inverses of one another. So It says determine whether they are. So this question kind of suggests there's maybe a yes or no possibility here. If it says verify, then I can guarantee that they are inverses, and you are simply showing that they are. Okay, so this question is worded in such a way where, who knows, it may not be. Let's try it. Let's find f of g of x. Watch how this works. 4 times input minus 8. That's the outside function. And inside, I'm going to put the g function, just like we did earlier. Now I do the distributive property here, and I get x plus 8, and then we have that minus 8 at the end. And look at that, it all comes out to be x, just like I said I needed it to be. And I put a little check mark there to show that it worked out. Now I reverse things, and I do g of f. So 1/4 times the input plus 2. And in here, I'm going to put 4x minus 8. Again, I do my distributive property, and I get x minus 2 plus 2 equals x, check mark. All right, that looks great, right? So yes, I verified that yes, it's an inverse. Okay, moving on to 9 through 10. Now the directions are a little different here. Earlier, we solved equation. That's where we get numbers. We get like x equals radical 10, right? Remember getting that answer earlier. Simplifying simply means reducing fractions, getting things out of radicals, canceling anything that's on the top and bottom if there's some factors there that can cancel and such. So we're going to be rewriting this in a more simple form. Now, to simplify a radical, I've got a couple different videos on this because there's one really great way to do this. It's called finding pairs. But since this is a fourth root, we're going to find groups of 4. So for this very first problem here, I'm going to tear this apart for you. This is 2 times 2 times 2 times 2. This is x times x times x times x. And then for saving some time here, I'm going to write y to the 4th times y to the 4th. So we're looking for groups of 4 because it's a fourth root. Any group of 4 can make a jailbreak, make their way out of the radical, and then be simplified. So for example, this group of 4 comes out of the radical and it becomes just a 2 to the 1st on the outside of the radical. All right, we don't have 4 of them. We only have 1 on the outside of the radical. So it made a jailbreak. This guy right here, we got 4 factors of x. So again, they make their way out. We have a y to the 4th. So that's 4 factors of y. So what do we put on the outside? We put a y to the 1st. All right, and then we have a second factor of y that makes its way out. So we end up with a y squared. There's nothing left under the radical in this question, so we don't have to put fourth root of anything. It's just going to be our answer right here, 2xy squared. That's called simplifying a radical. Now, a different way to do it is you can divide. 8 divided by 4 is y squared. 4 divided by 4, 1. There's one group of 4, right? Division is just finding groups of. And then 16. We don't do 16 divided by 4. You ask yourself, what to the 4th power is 16, and it ended up being 2. So it made its way out there. So that's how you could do it without writing all these factors out. Adding and subtracting. Any sort of terms in algebra, when you're adding and subtracting, they have to be like terms. So you need like terms. Think of it that way. So we're going to simplify things and hope that maybe there's some like terms. Like this is radical 25 times radical 2. So that's 5 radical 2. So if I bring this 2 down here 2 times, I get 10 radical 2 on this first term. That's called simplifying a radical. You can also, instead of finding pairs, just look for perfect squares in this example. That's the way I do this, is just look for perfect squares. This one is radical 9, radical 5. So that's 3 radical 5 on the second one. And the third one is 9 times 2. You really have to know your multiplication facts, right, while you're looking for perfect squares. So you just kind of rack your brain. Does 4 go into it? No. Does 9? Yes, it does. 9 times 2. So that's 3 radical 2. And oh my goodness, look here. We have like terms. Boom, boom. So that is 13 radical 2 plus 3 radical 5. Now, are we done? Trick question, folks. Yes, we're done. I know it's so tempting to then think or feel like you have to write radical 7, but these are not like terms. It's sort of like 13x plus 3y. Would you write 16z or something else? No. You would just say, that's my answer. Okay, so this is my answer. Radical 2 is not the same number as radical 5, so it's as though they are different variables, x and y. They can't be combined, and we're done. All right, moving on. Number 11, let's use our division facts. All right, so let's start with z. How many times does 3 go into 6? 2. So we're going to get a z squared on the outside of the radical. Let's back it up. How many times does 3 go into 4? 1 time with a remainder of 1 factor. So I'm going to have a y in here, and I did have one group of 3. Remember, I asked you 4 divided by 3 is 1, remainder 1. So one group made their way out. How many times does 3 go into 7? 2 times. So we put an x squared on the outside, and we have a remainder, 1 factor, underneath. Now, you have to ask yourself, is there anything to the third power that equals 54? Well, you could take 54 and just start splitting it up, right? It's 2 times 27, and then this is 3 times 3 times 3. Aha! There we go. This is a group of 3. It's 3 to the third power. So 3 makes its way out, but this 2 sadly has no friends, so it's stuck inside the radical there. So 2xy. That's called simplifying. We got everything out of the radical that we could, but there were some remainders this time, unlike that earlier problem. Okay, so that's the end of the second page. We're cruising right along here. Hopefully this is helpful for you. Reviewing radicals. Also radicals, but what's different here, folks? Read the directions. What's different? Are we simplifying? We're actually solving. We're going to get an answer this time. X equals. We may get multiple answers. Who knows? So we have to follow the order of operations in reverse, PEMDAS. So you always ask yourself, can I add or subtract something away from this variable? Nope. Can I multiply or divide something away? No, not really. All right, so we've got sort of a grouping symbol in a way here. How do we get rid of that fourth root? The inverse of a fourth root is a fourth power. So I'm going to put a fourth power on both sides. So whatever you do, you have to do to both sides here. Again, we're not simplifying. We're actually doing things to both sides so that we can isolate the variable. This would be 81, 3 to the fourth power. We subtract 1 on both sides, and we are home free. So that first step was the only tricky step there. K equals 8. That first step was the tricky one, to go ahead and put a fourth power on both sides. Number 13. What are we going to do here? Well, this is a good chance for me to remind you about rational exponents, and we're going to have more problems on this in a moment. Rational exponents mean roots are going on. This is a root. So I could rewrite this problem. I'm going to divide both sides by 4 first, though, because that 4 is outside that parenthesis. So we can get rid of that 4 just on this first step. So we end up getting 5 on the right side. Just for purposes of explaining this, I'm going to rewrite the left side as a fifth root, because a rational exponent is really a root. What's down low is your root number, because remember, roots are underground. They're down low. So the number on the bottom, on the denominator, is your root number. Now you probably know what to do, right? Because we went over this on the last question. We're going to raise both sides to the 5th power. So we get x plus 2 equals 5 to the 5th. We then subtract 2, and we get our answer. X equals 5 to the 5th minus 2, and you could type that in your calculator and get the answer. All right, so this problem is real similar. So you might want to pause the video and give this a try now, because it's real similar to the last one. Always start by moving things to the other side, getting rid of things before you start doing exponents and stuff. Subtract 6 is the first step here, folks. And I would encourage you to think of this as a third root, which means you can raise both sides to the 3rd power, which is 27, 5x plus 7. You can then subtract 7 on both sides. 5x equals 20. So x equals 4. X equals 4. Only one answer, and that would be it. All right. So now we're going to go back to the concept of composition of functions. It says we have a defined function, and it has the word solve here. It doesn't say simplify or find. It says solve. Solve an equation. Look here. We have an equal sign. We have a left side, and we have a right side. So the right side is 3x plus 8. This is a question that deals a lot with reading carefully and understanding what it's saying, what it's asking you to do. Solving an equation. So the right side is 3x plus 8. What do we have on the left side? We have g of g. G. That's not so hard, right? G. 3x plus 8. There it goes. It's inside. We then do our distributive property, launching our missiles here. And we have an equation with variables on both sides. Again, back to pre-algebra times when life was good, right? When life was easy. We have variables on both sides, so this is 32. I encourage students to always deal with the variables first. It can prevent some silly mistakes. And I like to stay positive. If you know me, I like to stay positive. So I decided to subtract 3x because I saw it would create a positive 6x over here. It's just one less negative sign to deal with. Subtract 32 on both sides, and I get negative 24 equals 6x. X equals negative 4. So there's our answer. So we solved the equation, but we had to really decrypt what this meant. We had to write the equation that was written in the question. That's a good question. I like that one. Number 16, determine whether this function is exponential growth or decay. All right, exponential growth and decay, you look at that base, that growth factor there, and I see that that is bigger than 1. It's bigger than 1, so it's growth. If it had been like 1/3 or 2/5 or something like that between 0 and 1, it would be decay. All right, write the equation in logarithmic form. Here we're going to be writing between the two forms like we did earlier in solving the equations. So we write log. By the way, this is a true statement, right? 5 to the negative 4th, if you type it in the calculator, is a small number. Negative exponents mean fractions. It means 1 over 5 to the 4th. Just a reminder on that. So log, what is the base? The base is 5. Answers to logs are exponents. So we make that exponent nice and big now. And then inside the logarithm, I like to put a parenthesis here just to remind you that this is a function. It's a log base 5 function, and inside that function is the number 1 over 625. Make sure you write this 5 nice and small. Again, a lot of students write a giant 5 here, and then they put the 1 over 625 as an exponent. That's not right. That's actually wrong and will get marked wrong on your test. Look at that. We're done with another page. We're just cruising right along here, folks. Number 18. Solve. Follow the directions. We're solving equations again. So we have a left side, we have a right side. Our variable is stuck inside a logarithm. So what are we going to do? We're going to rewrite it in radical form, or in exponential form. I was thinking about the next step. This is actually a radical. We're going to rewrite it in exponential form. So exponential form first, and see if that helps us. That gets the x out of the log, which is why I knew to do that. So 64 to the 2/3 power is our answer. Now, of course, you could go to your calculator and type that in. Just be careful of using parentheses and things. But this is a great reminder that the number on the bottom is your root. This is the 3rd root of 64. And then the number on the top, folks, is an exponent on that. So if this were on a no calculator section of a test, you could do this. I'm able to do this and get 16 because I happen to know that 4 times 4 times 4 times 4 is 64. 4 times 4 times 4 is 64. So it works out well there. 4 squared is 16 then for the final answer. Okay, what about this question? What could we do here? Well, we could use logarithms, but there is another way to solve some equations, and that is to get a common base. So that's personally what I would do here, because I see that they're both divisible by 3, and in fact, not only divisible by 3, but that 3 squared is 9. So I'm just rewriting the left side. You see how I'm changing the base? This is called changing the base. And then the right side is 3 to the 5th power to the x plus 2. So 243 is the same as 3 to the 5th power. 9 is the same as 3 squared. Now that the bases are the same, you can just solve the exponent equation. Let me come over to the side here. So if a to the x equals a to the b power, then x equals b. If the bases are the same, then you just set the exponents equal. That's why I chose to get the bases the same, because it really does make our life pretty easy here. We now have 2 times the quantity, 3x plus 4. Now, why am I writing 2 times the quantity? It's because when you have a power of a power, you multiply. When you have a power of a power, you multiply. So we get 5 times the quantity, x plus 2. So this would be 6x plus 8 equals 5x plus 10. I'm going to move quickly now because this is all super simple for you, right? I'm going to subtract 8, and while I'm at it, I guess, I get x equals 2. And you want to go ahead and plug that in up above, and you'll see indeed that it does work. Number 20. Okay, here we have a log equation. So we have to remember that whole unit we did on properties of logs here, because I really want to condense this, was the magic word, which means combine them into one logarithm, because then if the two sides match, I can just solve what's inside. You'll see. So do you remember how this works? When you have log A plus log B, it is log A times B. And I've got like 3 or 4 different videos on properties of logs if you need to check those out. So we can combine into one log by multiplying. So this becomes log base 3 of, I'm going to put a big bracket here just to make it super clear, that x minus 3 and x plus 2 are going to be inside that logarithm there. Then we can just go to the next step, which is just solve the inside equation here because the log base 3 is on both sides, it's kind of irrelevant at this point, except we do have to make sure we stay within domain requirements. So how do we solve this quadratic equation? This is a good review of quadratic equations at this point. How do we solve this? We need to multiply or FOIL out that left side, move the 6 to the left side so it merges in so that it's equal to 0, and then factor again. So we have to multiply, merge in the 6, and then factor again, and we'll see what happens. So x squared minus x minus 6 equals 6. We subtract 6 on both sides. We get x squared minus x minus 12 equals 0. We then factor x minus 4, x plus 3. I've got tons of factoring videos, so if you need to go check out some of those, remember how to reverse FOIL, please do so. And we then set each factor to 0 separately. So sometimes you have to solve a little mini equation. These are so easy that you probably can do it in your head. I know you can, in fact. And we get the answers 4 and negative 3. Now, we should really go back up here and make sure that these answers are allowed to be used. And I think maybe one of them needs to be thrown away. The negative 3 needs to be thrown away because if you plug in negative 3 in here, it causes a negative inside the log. Causes a negative inside the log, and that's not allowed. If you graph the log base 3 function, you'll see it does not exist in quadrants 2 and 3. So x is not allowed to be negative. I'm sorry, the stuff inside the logarithm is never allowed to be negative. It's outside the domain. So we got to throw that away. X can't be negative 4 either, by the way, or negative 1 or even 2. So x equals 4 is the only solution. So that was a good question because we had an extraneous solution, an extra solution that's not really a solution. Why, by the way, why does that happen? Why does that happen? How do we get an answer that can't be an answer if we followed all the correct steps? Well, the answer to my question is we threw away information right here. When we got rid of log base 3, we threw away information and we solved a much more simple equation. But then before going on, we have to sort of dial back and look at the original question and just make sure that those answers answer the much more sophisticated question. Hopefully that made sense. All right, number 21 here. What are we going to do here? Once again, we're going to condense, but this time it's subtraction. Do you remember what the rule is, what the property is for the subtraction? So log base A minus log base B is log A divided by B. So instead of multiplication, you do division inside one log. So let's write that out. Log base 6 of 5 minus 2a all over 3a is 1. Now let's just rewrite this in exponential form then. The base, the exponent, and then what's inside the log. Then, personally, I would just solve this proportion by cross-multiplying. You solve proportions by cross-multiplying. So 18a equals 5 minus 2a. So 20a equals 5. A equals 5/12 or 5/20, which is 1/4. 1/4. And I'm going to circle that. Remember, we have to go back and make sure we're allowed to use 1/4. Basically, just need to make sure it doesn't cause the inside to be negative, and it's fine here, and it's fine here. So we are good. That's our answer, 1/4. This next one's super simple, although it does have some complicated factoring, I guess. Good one to talk about. For what value is this undefined? So rational expressions are undefined when? You're never allowed to divide by 0. Like 5 divided by 0 is undefined. 10 divided by 0 is undefined. Anything divided by 0 is undefined. So you only have to figure out when is that equal to 0. Right? And those will be what I like to call the problem children, those extra answers that can't be answers, or those numbers we need to stay away from that are outside the domain. So 2x squared minus x minus 10 equals 0. All right, so factoring this is a little bit more difficult. I think you can still guess and check it if you have enough experience on this, which you do, I'm sure. This would be 2x and x. It has to be a plus or minus. I may have to switch these plus or minuses in a second. We'll see. And whatever I put here and here has to multiply to be negative 10. So let's try some different things. Let's try 5 here and 2 here. Does that give us the negative 1 that we want? Well, we get negative 10 plus 2. Nope, that's not it. So I'll let that fade away. Now, let's try it the other way. What about 2 here and 5 here? That's 5x minus 4x. Aha, that's really close. That's 1x, but I want negative. So I got to switch these signs, folks. This is going to be plus. This will be minus. I'll put my 4 here. Put my 5 here. And my 2 here. And now, if you FOIL it out, you see how it gives you that negative x that we need. All right, now we set each factor to 0. 2x minus 5 equals 0. X plus 2 equals 0. So x equals negative 2 is one of the answers. So this is a great example of where you could probably do this in your head, or maybe you need to just solve the little equation, and that's okay. So you write the equation down, and you solve it. 2x equals 5, x equals 5 halves. Now you do need to, these are the numbers that cause it to be undefined. So I like to tell students to put the little not equal to, like it's not allowed to be equal to. Those are our, quote, problem children, our values that are outside the domain. Okay, another page under our belt, folks. Now we're going to be simplifying rational expressions. Add, subtract, multiply, divide. So adding and subtracting is kind of similar. Multiplying is probably the easiest, and dividing has an extra little trick into it. We always factor in cancel as well. So how do you divide fractions? A lot of students, I swear, fractions are their kryptonite. It's just what makes them just shrink down and give up for some reason. So how do you divide fractions? A lot of students learn keep, change, flip. Keep the first fraction the same, change it to multiplication, and flip over the second one. So I'm going to keep the first fraction the same, and I'm going to factor as I go because that just saves some time and space. This is a special factorization. This is x plus 5, x minus 5. Notice if you FOIL that out, there's no middle term. I'm going to change it to multiplication. So I'm going to change it to multiplication. That's my keep change. And then I flip over the second one, factoring as I go. There's really no factoring to do here. All right, now before I multiply the tops and I multiply the bottoms, because that's how you multiply fractions, I'm going to cancel. So this factor here cancels this entire factor here. We have an x and an x squared. And that cancels 2 of the factors that are on the numerator on that first fraction, leaving us squared. You now multiply across, left to right, the top and bottom. There is no butterfly or crossing here. Okay, it's across the top and then the bottom. And because we canceled everything, our answer should be in simplest form. So that's what we mean by simplifying. So keep, change, flip on division, folks. Number 24, multiplication. But this is a mess. We need to factor first. Always factor first. And don't forget about GCF. Don't forget about greatest common factor factoring. A lot of students forget that for some reason. So m plus 4, m minus 2, that's not so bad, the top there. The bottom here is 3 times the quantity. This is what I mean by GCF. We can divide them all by 3, which makes all the numbers smaller and helps us get the factorization, of course. Times, these are both divisible by 4. And then these are both divisible by 8. And what else? M. Also m. So m minus 4. Or sorry, yeah, m minus 2. m minus 2. What do we do next? We recognize that this is not factored completely, and that can also factor some more. So let's keep going. Again, these expressions, by the way, are all equal. That's what simplifying is writing equal expressions that are merely simplified and reduced. It's like reducing fractions. Oh, I actually put an x. m plus 4, m minus 2, all over 3 times the quantity, m plus 4, m plus 1, times 4, m minus 1, m plus 1, all over 8m, and then m minus 2. All right, so I've canceled that with that. I've canceled that with that. Is there anything else that can cancel? Well, I see another one. M plus 4s, right? You're probably screaming at your computer right there, or your phone. Anything else? There is one more thing. This 4 and this 8 simplify to be a half. So I'm going to put a 1 on the top and a 2 on the bottom. So this would equal m minus 1 all over 6m. And we get our answer here. So nothing else left to do. So we canceled a whole heck of a lot of stuff, didn't we? All right, moving on, number 25, adding and subtracting. How do we do that? In order to add fractions, you have to have a common denominator. And I like to think about it as upgrading the fractions so that they all match. So make sure you use plenty of space while you're doing this. It is important to factor first still. We still have to factor first so that we can step back and see what we're working with. So this is 3 over x minus 3 minus 18 over x plus 3, x minus 3. Notice that this already has, they both already have the x minus 3, I meant to say. So we need to introduce this one over on the left side so that it matches. And then whatever you do to the bottom, you have to multiply on the top also. So then some students get confused here and they think, well, what do I do next? Do I cancel the x plus 3? No. We put them there for a reason so that we can combine it into one fraction now. 3 times the quantity x plus 3 minus 18, all over the common denominator. And no, the x minus or plus 3s still don't cancel, folks. I get that question as well. We launch our little missiles there, distributive property. We get 3x plus 9 minus 18, all over x plus 3, x minus 3. We then get 3x minus 9, all over x plus 3, x minus 3, which is a lovely answer, but you might lose a half a point if you leave that as your answer because this is not fully simplified. When you add or subtract, at the end, you have to simplify. So you have to look for any factoring, and the top has a 3 that can come out. So now that cancels that. There's the fully simplified answer. 3 over x plus 3. Okay, we got to get common denominator here, and you might think that these are completely different denominators until you look more closely and realize they're kind of similar, right? They both have a 2n, just the signs are different, and they both have a 1, the signs are different. So the way you get them to be the same is to recognize that you can factor a negative 1 out of one of them. And now they look really much more similar, right? We then introduce a negative 1 here and here, or you could actually cancel the negative 1 and the subtraction if you want. I'm just going to stick to the same process as I did on the last one, so hopefully it'll be less confusing. Now the denominators match, and I can write negative 3 minus 2 on the top, all over negative 1, 2n minus 1. That's negative 5 over negative 1. 2n minus 1. Now cancel the minus sign. So you get 5 over 2n minus 1 is the most simplified form. All right, cruising right along. That's a nice question with a little negative 1 trick. Here we have 3 fractions, and the denominators don't match. So you have to analyze what each one has and what each one doesn't have, and what the least common denominator is. So the first multiple that 5, 6, and 3 has in common. The easiest way to do this is to recognize, well, I know they're going to all need an x, right? That's easy. What about the numbers? Let's start with the biggest one. Does 5 go into 6? No. Okay, so 6 can't be the least common denominator. Now double that. 12. What about 12? Nope. 12 doesn't divide by 5. What about 18? Nope. And you keep going until you get to 30. 30 is the first, so the LCD here is going to be 30x. So we're going to upgrade them all to be 30x. So I'm writing this a little differently, or helping you, maybe this will click for you a little differently than the last one. So that's our goal, is to get them all to be 30x. So what's it going to take to get there? This will be multiplying by 6 over 6, so that's a 12. This one's going to need a 5x. So we're going to get 25x there. And then the last one simply needs a 10. So that's going to be 20. So we end up getting 12 plus 25x minus 20 all over 30x. So that is negative 8 plus 25x all over 30. Now before I circle it, I always look and see, is there any factoring or canceling that can happen here? And this is only divisible by 5, and these guys are 8 is not divisible by 5. So that is our final answer. We'll go ahead and circle that. We simplified it. We weren't solving an equation. We're not solving for like x equals 3. We're simply simplifying. All right, that's the end of that page. All right, fill in the blanks, identify the parts of these rational functions. All right, so lots of big words here, and each one comes from a different aspect of the function. All right, let's start with, we'll go ahead and start with horizontal asymptotes. Again, you could graph these and kind of, I guess, quote, guess where the horizontal asymptote is. Or you can recognize that the bottom has a bigger degree. The exponent on the bottom is bigger, so the bottom will be infinitely bigger. So as time goes along, this is going to approach 1 over infinity, which is essentially 0. Y equals 0 is your horizontal asymptote. So because the denominator was bigger, you have a horizontal asymptote of y equals 0. I'm going to erase that to get that out of the way. X-intercepts. X-intercepts are always of the form something comma 0. So it's when y equals 0. So when does y equal 0? It's when the numerator is 0. Okay? So x equals 6 will be a possible x-intercept. Now, I say possible because I think I want to factor this bottom before I go any further, just so I know what I'm looking at here. So x minus 6 and x plus 4. Uh-oh. Do you see how we're going to actually have a whole at x equals 6, because wholes are numbers, it's those problem children that I mentioned earlier in the video, those values that can't go in. So there's a hiccup in the graph. It could be a whole or an asymptote. This turns out to be a whole because this factor cancels the factor in the top, causing it to be an excluded value, not an asymptote, but an excluded value at a whole. It's called a discontinuity in the graph. So it's a whole. So that also means since it's a whole, it can't be an x-intercept. So the graph doesn't hit it there. The graph does not exist at x equals 6, so it can't be an x-intercept. So this is a trick question. This would be none. There aren't any values for x-intercepts. Vertical asymptotes come from those, quote, problem children, those excluded values in the denominator, where it doesn't cancel in the numerator. You see how there's no x plus 4 in the top? So this would be x equals negative 4 is your vertical asymptote. Excuse me. All right, and then domain is everything but the problem children, is what you say here. Everything but the excluded values. So you would write negative infinity all the way up to negative 4. Remember, we're skipping that. Negative 4 all the way to 6. We're skipping that. That's why I'm using parentheses, because I'm leaving it out of my interval notation, 6 to infinity. Always start with your smallest number first, which is negative infinity, and then go left to right. Generally, myself and other teachers will also accept something like all real numbers except x equals 6 and negative 4. Or I often like to put that not equals there. All right, the range is up and down. I encourage you to graph this on your graphing calculator and see. But there are, I believe, I don't have my graphing utility here. It's going to be all real numbers except y is not allowed to be 0 because we have that horizontal asymptote there. All right. There's also, so I think that's probably the answer. Again, I would want to go to the graph and verify that. Figuring out range is much easier to do when you look at the graph. Now, the y-intercept. The y-intercept is always a point 0 comma something, over 0, up or down something. So you literally plug 0 into the function, 0 minus 6 over 0 squared plus 2 times 0 minus 24. And what do you get? You get negative 6 over negative 24, which is positive 1/4. So it looks like 0 comma 1/4 would be the y-intercept. So that's how you find those 7 things. Okay, and we have another example here where it is sketching the graph. Oh, it says also sketch, so I didn't do that. So you'd have to, I'm sure you could do that as far as sketching those based on all that information that I gave you. All right, horizontal asymptote. Again, you see how the denominator is bigger than the numerator here, but this shifts the entire graph down. That's a downshift by -3, a vertical shift in the negative direction. So y equals -3. Instead of being y equals 0, it gets shifted down. We have a vertical asymptote at x equals -4. I know that because there's no left-right. I'm sorry, there is a left-right shift here sort of going on, but that's okay. Don't worry about that. Just understand that x is not allowed to be -4, so there's going to be a vertical asymptote here. All real numbers except x can't be -4. And the range is going to be all real numbers. Y is not ever going to be -3. And the transformations here are it is a down by 3, it's left by 4, it's a reflection because of the negative sign, and a amplification or a stretch by 2 because of that 2. So those are the transformations. Okay, numbers 30 and 31, we do have a graph here, so we'll be able to sketch these a little bit. Horizontal asymptote, again, y equals 0. The reason is because the denominator is bigger than the numerator. So I'm going to go ahead and put that asymptote in there, folks. There we go. We got our horizontal asymptote in there. X-intercepts. X-intercepts are at over something up 0. So it's when the function spits out 0, which is never. So this will be none. Do we have any holes? Well, let's see. We're going to factor the bottom. It's x plus 5, x plus 2. But neither of those factors cancel anything in the top, so no holes. But we do have two vertical asymptotes at x equals negative 5 and x equals negative 2. So I go to negative 5, and I go to negative 2, and I'm starting to get all my regions here, right? I've like separated this into 6 regions of the graph now. The domain, of course, is all real numbers, or you could use interval notation just for purposes of time, except x cannot be negative 5 or negative 2. All right, the range here is y is everything except 0. Now the y-intercept, remember how we plug in 0, so we get 3 over 10. 3/10 is the y-intercept. So I could come up here to 3/10 and put a little dot. There's my y-intercept. So that's kind of helpful because that tells me that this region of the graph is like that. Okay? Now, what else is going on here? Do you remember how we have no x-intercepts? We have no x-intercepts in this thing. So that means the graph cannot look like this, because then we would have had an x-intercepts. The graph cannot look like this in here. The graph can't look like that over here either. So instead, what I'm going to do is just plug in a number. Let's plug in, I don't know, negative 3. Let's plug in negative 3 into the function and see what we get. Do we get a big positive or a big negative? So this would be 9 minus 21 plus 10. This is negative 3 over, negative 3 halves, right? Again, you could go to your calculator and just see where this is at, but I'm trying to do this without a calculator at this point. So it's negative. What did that just tell me? It told me that the graph is down here. So it's going to look something like that down here. Now, what about plugging in a really large negative number so that we can see, does the graph exist up here? Or do we get a negative, in which case it'll exist down here? So just imagine plugging infinity in here. Well, this is going to be a positive here. Negative infinity. Whenever you square a negative, you get a positive. So it will end up being a positive, which tells me we're going to be above the x-axis and up here. So I was able to sketch it roughly, even without a calculator. Okay, and also just reiterating, since there were no x-intercepts, I knew it didn't look like that. It had to be a U-shape below. All right, I think we have one more graph here. Now this one, do you see how the degree on the top is the same as the bottom? So then we have a horizontal asymptote that is the ratio of the leading coefficients. It's a fraction from the leading coefficients. A lot of students struggle with that. So y equals 1 is your horizontal asymptote. So I'm going to put my dotted line there at y equals 1. Now, x-intercepts are always something comma 0, and they come from the numerator here. It says 0 on the function. Remember earlier we said find the zeros, and we just looked at the top. So x equals 0 is an x-intercept. So I'm going to put this is 0, 0. We got a dot right there, and by the way, that's also the y-intercept then, right? And so that's also the y-intercept, because if you plug in 0, you end up getting 0. So they end up being the same thing in this question. Now, are there any holes? Does x plus 2 cancel anything in the top? Nope, it doesn't. None. There is a vertical asymptote, though, at -2, because that's our, quote, problem child from the denominator. So I go to -2, and I put my dotted line here. Okay. And the domain here is x is not allowed to be -2. And the range is at y is never going to be 1, because we only have one horizontal asymptote and there weren't any holes elsewhere. All right, so what does this graph look like? So again, I would, we know that we have an x-intercept here, so that makes this side nice and easy. And then personally, I would imagine plugging like negative bazillion into this thing, and I get a number that is, so negative infinity all over negative infinity plus 2. That's a number that's actually bigger than -1. That's a number that's bigger, bigger than +1 is what I meant to say, because the denominator is actually smaller than the numerator, it's bigger than 1. So that tells me that it's up here. So you could have maybe plugged, maybe it would have been better for you if you'd plugged -4 in and then you get a value up here somewhere. Okay, so there's a rough sketch of the graph. All right, we've just got a few more problems here to do, and then we will be done. Number 32, solving an equation. All right, there are a couple ways to do this. You could add these or subtract these, and then you could do a proportion and cross multiply. That might be the easiest way. Or you could get all the denominators to be the same, which is probably what we want to do here, because this would be 2x minus 3. You see how we could upgrade, quote, upgrade them all to be 6x minus 3. So we're going to upgrade them all to be 6 times x minus 3. Okay, so this one here needs a 6, so I'm going to multiply by 6. So this would be 12x. This one here is going to need a 2, but it's also going to need an x minus 3. And then the third one simply needs the number 3, the factor 3 multiplied in, so that leaves 6. The reason I got all the denominators the same is now I can just throw away the denominator and solve the numerator equation, which is 12x minus 2x plus 6 equals 6. So 10x equals, if I subtract 6, don't panic here, folks. We got 0. It's okay. 0 is a number. We divide by 10, we get x equals 0, and that might be our answer. You always have to check that it works and that you're even allowed to plug it in. And if you plug it in, it does work and it's allowed to be plugged in. It doesn't cause the denominator to be 0. Because remember, sometimes when we throw away information, we might get an extraneous solution. But that did not happen here. We got the answer. All right, explicit formula for the sequence here. Do you see how this is going down by 7 each time? Down by 7. So any term is always going to be, so we're going to start with 98, and then we're going to add -7 times n minus 1. So let's check that I did that right. I always have to kind of think about the formula. I don't necessarily have these memorized because I don't work with these a whole lot. So let's see if this works. So a sub 1 would be 98 plus negative 7 times 0. So that just goes away. And you see how we did get our first term. That's what that sub 1 means, the first term. Now let's do the second term. 98 plus negative 7 times n minus 1 would be 1 this time. And you see how we do. We get 91. So it works. So there's our explicit formula. You could write it a couple different ways. You could write 98 minus 7 times the quantity n minus 1, or you could even distribute property and simplify it from there. But there's the formula. All right, so what's going on here? Well, if you take and divide, I think what you're going to find is that negative 3, dividing by negative 3 is the common process here. So that means negative 1/3 is the base in our exponential. So any term is going to be the first term, which is 486, times negative 1/3 to the n minus 1 power. And you might be wondering, why is it n minus 1? Well, let's just find those first couple terms and hopefully you'll see. See, this first term, we want it to be an exponent of 0 because anything to the 0 power is just 1. So you see how we get the first term then. We got 486 because we did the n minus 1 up there. That caused the exponent to be 0. All right, let's do the next term. A sub 2, the second term would be 486, and then our base would be negative 1/3 to the first power, and if you type that in your calculator, you get negative 162, and then you can keep going from there. Okay? All right, so finding the 23rd term, I'm going to just find the formula here. You see how it's going down by 7 again. All right, so this would be an equals 98 minus 7 n minus 1. So that was our formula from earlier. So then we just plug in 23 into our formula and use our calculator. Easy peasy. So this would be 98 minus 7 times 22, whatever the heck that is, and you can find it. Okay? And then this one here, our formula was 486 negative 1/3 to the n minus 1 power. So we're going to find the 10th term. So a sub 10, that's what that means. The 10th term equals 486 negative 1/3, and then you do an exponent of 9 because of the n minus 1. All right, very good. And that's the end of the document, folks. That's a review of semester 2 of Algebra 2. A lot of good material here, a lot of good examples. So hopefully you found this video useful. Don't forget to subscribe to my channel, like this video, and comment down below. Maybe I made a mistake. In fact, probably I made a mistake somewhere. So you can point that out in the comments. Not that I can go back and fix this, but hey, I appreciate it. All right, until next time.